Hello, welcome to GeoAI tutorial number 15. In this video, I'm going to show you how to train a deep learning model from scratch for car detection using the GeoAI Python package. Before we dive into the source code, I would like to show you the results. So this is the car detection result using the GeoAI package and using the model that we trained from scratch. So you can see the red outlines the car detection result, and looks pretty good. And all we need is just a couple lines of code to train the model from scratch, and then you can use that to do inference on any high resolution aerial imagery or satellite imagery. So look at this, and everything is automated. Of course, it's not going to be perfect. You might still need to fine tune the parameters to get better result, but just at the initial result, look at here. I think it performs pretty well. So let's dive into it. I'm going to show you from scratch how we can get it done. So you need to go to the GeoAI website, and then from here on click examples, scroll down, find train car detection here on the left, and then click. You can either run this one using Google Colab, or you can download this one to your computer. So if you want to run in Google Colab, open this one, and then click runtime, change runtime type, and then select T4 GPU. It'll be so much faster. Then after that, you can just uncomment the first code block to install the package. Then you can run from the beginning to the end. I have already set it up on my local computer, so I'm just going to run it on my computer. Actually, previously I already created a tutorial. I think it's number 8. Show you how to actually do car detection, but at the time I used the ArcGIS pre-trained model. And so a couple days ago, ArcGIS actually reached out to me, asked me to take down all the pre-trained models. They do not allow me to use that because of the licensing issues. It cannot be used without ArcGIS. So I spent the past few days retraining the model from scratch. So now we have our own pre-trained models, and you can use it for free without limitation. And you can do it, use it to customize, fine-tune your model for any other location around the globe, and then you can use for car detection without using commercial software. So this video, I'm going to show you how to do that from scratch. I'm going to go to the very beginning here. Also, you can look at the model here. You can just take you a couple minutes. You can train the model, and it has pretty high accuracy. For example, IOU ranging from 0.86 to 0.9 something. So it's very high accuracy. And you can either use my pre-trained model, or you can train the model from scratch. So let me show you from scratch. I'm going to start from the very beginning. And so the first step is to import the libraries. Okay, and then we're going to download some sample data. So I provide some sample imagery here, high resolution aerial imagery. I also want to provide the training vector data. So I created this vector data by myself, so they can use it also for training. And then I also provide testing imagery, so they can test the performance of the model. Once they have this, let's download the data using the download file function, and all the imagery has been downloaded to the computer. After that, let's take a look at the data. So use the view vector interactive. We can look at what the data looks like. So this is the training data. Behind is an aerial imagery, 7 centimeter, and these are all the training data. So the blue outline here represent the training data. So I create the training data, clean it up, and these are high quality training data. So you can zoom in to take a look at all the kind of the bounding boxes surrounding all the cars. And I remove all the false positive detection. And this is a pretty good one. And all you need basically just, if you are doing that for other area, you can also just have one imagery and then one vector data. So this is any vector data supported by GeoPandas. So it can be a GeoJSON, it can be a straight file, or it can be any other vector format. So one imagery, one vector data, or you can have a provide raster mask as well. So in this case, this is the data that we have. And then we're going to use this one for training the model. Again, you can zoom in, you can see the result here looks very nice. So also we can take a look at the raster imagery, the testing data. So this is an imagery in a similar to this area, but it's beneath it. And so you can also see all the cards here. So what we want is to train the model using the imagery and the vector data here. Then we're going to apply the model to do the detection of cards in this area and see how it performs. So the next step is to create the training data. So similar to the previous tutorials, what we need is just calling this function export geotiff tiles, and then specify the output directories and provide the input training raster data, also your training vector data, and then specify the tile size, the stride, and whether or not you want to buffer. You can use just all the default settings. Just run it. And so GeoAI, the package is going to take care of all the heavy lifting. It's going to basically create the training data, subdivided the raster into smaller tiles and also the corresponding labels. So if you want, you can actually find out here outputs and then images. So it's going to show here the summary, 544 tiles. So if you go to the directory, you should be able to find all of these in here. Scroll down to the end, it should be 543 here. So because it started from beginning, so total is 544. So these are all the images, and you can see the format is GeoTIFF. It also still has geo reference. Also, we have the labels, corresponding labels. So each image, you're going to have the corresponding raster mask. So under the hood, it's convert the vector mask to raster, and then so it's one-to-one relationship. It's a pair, basically image chips. Then with this, we can start training the model. We are going to use the train mask RCNN model. What you need to provide is the image directory where you have all the images. Also, you need to provide the labels and specify the output. So this one is going to be generated when we train the model. Specify the number of channels. Let me just run this one. So we're going to specify 10 epochs. By the way, so here I also provide the pre-trained model path. I already don't know to resume the training. So this is, if you already have some pre-trained model, I mean, it takes a while, and so you can resume the training if you want, if it's necessary. So for me, I'm going to start from scratch. So I'm going to delete this of this, and then let's run this one. So I'm going to start training the data using the image chips. So we have the 3 channels. You can change this one to more than 3. So if you have drone imagery, for example, hyperspectral or near infrared, you can change this number of channels, basically how many spectral bands of the imagery that you have. Base size, basically how many images you want to feed into the model all at once. So it's 4 images, and we're going to train using 10 epochs. The learning rate is 0.005. You can change this one if needed. And split basically means we're going to use 80% for training and 20% for validation. So this is all. You can just use or set all the default settings. Again, if you want to resume training or provide a pre-trained model, you can specify pre-trained pass, model pass, and specify the file pass, and also resume the training. Then you're going to start from beginning. But we're just going to start from scratch. So you can see from here, the first epoch, the accuracy, the IOU, the intersection over union, basically is the card detection mask divided by the over the union, basically the intersect the union of the two, the ground truth and also the prediction. So it's 0.68. The value range from 0 to 1. So the higher the better. That means your prediction aligns exactly as the ground truth. So if it is 1, that means it's very high accuracy. So in this case, you see the first epoch is 0.68. It's already pretty high just in the first trial. And after that, you can see it's increasing steadily. We are only training 10 epochs. If you have more time, you can train it a little bit longer, for example, 50 or 100 epochs. But usually you don't need that many, because once you reach a certain stage, the IOU is not increasing that much. So right now we already have 0.86. If we can reach 0.9, that would be great. And after that, you can just use that to do the testing. If the result is not good enough, then you can change it a little bit more time. So you can see in epoch 6, it's actually decreasing a little bit, but it should be fluctuating. So that means it's stabilizing. And so we're going to see what we get at epoch 10. So once you have this, then we can start running the inference. So the nice thing about this is when you're running the inference, you can run it in a large imagery. So you don't have to subdivide the imagery by yourself. GeoAI package will take care of that for you. So all you need is just passing whatever GeoTIFF that you have, and then just run the object detection, and that's it. So it's going to basically grab the imagery, subdivide them into smaller tiles, and then it's going to do the prediction. After that, it's going to actually merge the results for you, and after that, we can convert it to vector data. So let's wait for this one to finish. By the way, so you can specify earlier when we train the model, we specify the model output. So if you scroll up here, it's going to go to the output directory that we specify, and under the models. So over there here, you can take a look at the output directory and have the model passing here, zoom in. So here is the base model. So this is the one when the model is training, it's going to save the base model. So which model, whatever model that has the base IOU, it's going to be saved. So this is the one that's being updated when it's running the training process. Okay, so after that, you can also see here the final model path, and you can also see the training summary. So if you double click, you should be able to see the model trains 10 epochs, the base validation IOE 0.9007, and the final one. So this is pretty good. So that means 90% of the predicted mass overlay with the ground truth. And so this is the model that we're going to use, the base model. Again, you can save this one. So for example, I have this car detection USA here. So this is the one that I trained using 100 epochs. So you can also use this one to resume training. You don't have to train from scratch if you don't want to. All right. So once you have this, you can scroll down to all the way to the end. So you can see 0.907 and also 0.89. So it's pretty good result, just a couple minutes. Once you have this, now we can start running the reference. So again, we're just going to specify the model path. When we call this object detection function, you need to specify which model you're going to use. So we're going to use the base model, and the window size, the overlap, these are the same as the previous one. The confidence threshold is the one, the prediction. So this is the value range from 0 to 1. So the higher, the more selective. If you see many missing cards, then you want to decrease this number. If it is having too many false positive, you want to increase this number. And other than that, everything else remains the same. So just run this one. Under the hood, is going to subdivide this one into smaller tiles, and then it's going to run the prediction on each one. After that, it's going to merge all the mass as a single imagery. Okay, so once you have this, then we can convert this one to vector. We can call this orthogonalize function to convert them to bounding boxes. Otherwise, it's going to be a lot of ruggy edges along the border. So this doesn't look good. So what we want is to just convert the raster to vector, and you can set the epsilon. So this one controls how smooth of the boundary. So just run this one. It's going to convert all the vector data raster to, so in this case, we have 428 polygons. That means roughly 428 cards. After that, let's visualize. So call the view vector interactive, and this is what we have. So this is the testing imagery that we run using the model. Of course, you're going to see some of this like false detection here. You can actually remove them using some criteria, but look at the majority of the detection, and this looks pretty good, right? And you can turn the layer on and off to see the result. And some of the, for example, the outlines are still kind of ruggy edges. It's because of epsilon. So you might need to increase the number a little bit to make it more smooth, but the caveat is that you might also have some over simplified results. And also this is some of the cards actually under the tree is also being detected. So that's very interesting. And you also might see some of this. This can be removed because it's very thin. And I'm going to show you how to do that. So for example, this will be maybe the vector data, right? And what we can do is actually to, maybe we can add, let me show you here. I'm going to create a new code block. We can add geometry properties. So in this way, you can know the size, you can know the width, the height, or something like that. So let's just run GTF2 equal to maybe GTF GeoAI dot add geometry properties. So inside here is just provide the data. So it will be the geodata frame that we get from the raster to vector conversion, and that's it. You can use other default settings. Okay, so run this one. Inside here, view the vector data. I believe we can just pass in the GTF2 here. So, okay. So right now, if you have your mouse, you should be able to see all the geometry properties, right? So if there's something that's very tiny, you can set a minimum size to filter, basically just like a panda, so you can filter the smaller size. For example, this one, right? So the major axis length or the minor. So for example, the minor length is only 0.29. Let me see here, 0.29. So it's too tiny. In general, a car needs to be at least maybe 1 to 2 meters wide, and this one's too tiny. So you can actually filter this one if needed. So what you need to do, just go down here. Maybe we do this one. So we can say GTF, okay, filter, okay, and then filter equal to GTF2, and inside here can GTF2. For example, I can say what's the name again? Minor, okay, length. It needs to be greater than 1, for example. So, and after that, you will be able to get basically filtered result. Before we do that, we can just create a new code block and see how many, cards we have. So 399. So after we do the filter, let's see how many we have left. Oops. GTF. A minor length. So there's a typo here. Underscore meter. So the column name is not right. Underscore meter. All right. So now we have this. So we can type length and then GTF filter. Let's see, 389. So that means we filter out 10 of those cars that are too narrow. That means they might not be cars. And after that, we can visualize this again using the same approach. And you should be able to see now that one is gone. There might be still more false detection. For example, some of these you might need to remove them manually. But overall, look at the result. Looks pretty decent. There might be some missing one. This one I think is a little bit tricky. The color is not it's a little bit gray, similar to the background. The other thing you need to pay attention is on the right here. You will see some of the cars actually being merged together as a single one. And you might need to basically increase maybe the confidence threshold. So in this way, they are not, merging together as a single car. But overall, I think the result looks pretty good. You're welcome to adapt the model to your own area to see how it performs. And there's still some of this false positive detection here. This one, you can also use maybe the major length to remove it. So it's 2.6 meters. So if this looks like kind of square, you can look at the elongation. So the elongation is, for example, the value here is only 1. Usually cards are not really square. It should be maybe 2 to 1 over 2. So the elongation should be more than 2 because it's the length divided by the width. So most of the cards will be more than 2. Look at here, right? Elongation is 2.27. So you can also use that criteria to filter out those square polygons that are not cars. But you might also accidentally remove some of those that, for example, if the car park under the tree, and this one, the elongation is only 1.4. Nobody, because it only captures half of the car, not the full car. And you might need to be careful about all the criteria, but you can experiment with that and then get the best result once you figure out the best combination of criteria. After that, final step, we can also create a split map. So in this case, you can, so this one, I think the left layer, we're just using the initial one. So let me see if we can use the GTF filter. It may not work. Okay, it works. That's great. So we're using the one that we already filtered. And now we can take a look at all the cars that we detected using these methods. And this can be very useful if you have some drone imagery and you did create it acquired during certain event and you want to see how many cars on the parking lot, then this can be very, very useful. All you need is just a couple lines code, and then you can use the pre-trained model, and you can just run the pre-trained model to do the inference. Then you can quickly detect how many cars on the parking lot. Okay, so that's all for this tutorial. I hope you find it useful. I will see you in the next one.